Hello everyone, thank you for coming to my presentation. My name is Jizhong Yang. I am an associate researcher in geophysics in Tongji University. I'm going to talk about the application of least-squares reverse time migration with subsurface offset extension to vertical seismic profiling data. This is a collaborative work with Dr. Jingjing Zong, Professor Arthur Chen, and Assistant Professor Elite Li from National University of Singapore. My talk consists of these four parts. In the introduction part, I will talk about the motivation of this research. In the methodology part, I will give a short review on how to implement LSERTM mathematically. Next, I will use the simple layered model and the SIM model to perform LSERTM with both surface seismic data and VSP data. Detailed comparisons will be illustrated in this part. Finally, I will give a conclusion of this research. Let's first go through the introduction part. I would like to begin by this cartoon illustration for surface seismic survey and VSP survey. In surface seismic survey, both sources and receivers are deployed on the surface. In the VSP survey, the geophones are deployed inside the borehole, while the sources are excited on the surface. From this figure, we can see that the wave path in VSP survey is much shorter than that in the surface seismic survey. As a result, the VSP data have less NJ attenuation than the surface seismic data. Thus, higher resolution images can be expected from VSP data. This figure shows the comparison between the surface seismic image and the VSP image. Please note the higher resolution and more details in the VSP image, although the illumination area in the VSP image is much narrower than in the surface seismic image. These illustrations demonstrate that VSP has its distinctive acquisition geometry and can provide valuable information for seismic exploration. However, in field data application, velocity errors are inevitable in velocity model building because of the coherent noises in the seismic data, the simplifications we have made in physics during the processing workflow, and the opposedness of the inverse theory. Due to this fact, it is a good choice to utilize LSERTM because of its merit of fitting the observed data, even when significant errors are present in the migration velocity model. LSERTM has been actively studied for surface seismic data, but it is not reported with application to VSP data. In this study, we will focus on showing the difference in the behavior of LSERTM for the VSP data and the surface seismic data. In the methodology part, I will talk about some details in implementation of LSERTM. This is the extended imaging condition. Mig is the migration image. D is the observed data. Xs is the source location. Xr is the receiver location. FST is the source wavelet function. Jx minus h, xis tau is the Green's function from xis to the subsurface point x minus h. And Jx plus h, xr, t minus tau is the Green's function from xr to the subsurface point x plus h. When the migration velocity is accurate, the source side wave field and the receiver side wave field will meet at the same location at the same time. When the migration velocity is inaccurate, there will be a distance between the sunken source and the sunken receiver. The extended forward-borne modeling is the adjoint of the extended image condition, where the data and the migration image are interchanged. Here U is the forward-borne model data. The rest symbols are the same as in the previous slides. LSERTM is generally formulated as minimizing the L2 norm difference between the modeled data U and the observed data D. This objective function can be iteratively solved with the conjugate gradient algorithm. The above equations are the same for the surface seismic survey and the VSP survey. However, it is not necessary that the behavior of LSERTM is the same for these two surveys. Let's use some numerical examples to demonstrate the behavior of LSERTM for the VSP data and the surface seismic data. We first apply LSERTM to a simple layered model. There are in total 77 sources on the surface, with a source spacing of 50 meters. For the surface seismic survey, There are 401 receivers deployed on the surface with a receiver interval of 10 meters. For the VSP survey, there are 81 receivers at x equals 2000 meters in distance from z equals 200 meters to z equals 1000 meters at depth. The receiver interval is 10 meters. With this simple layered model, I will first show the illumination difference of surface seismic data and VSP data. Next, I will compare the kinematics of the subsurface of the geysers and the angle geysers. Then I will illustrate the difference in the stackability of the extended images. We first perform LSEITM with correct migration velocity model. The subsurface offset range is from -100 meters to 100 meters, as denoted as hx here. The front panels show the migration image at h equals 0. It is very clear that the VSP data have much narrower illumination area than the surface seismic data. The red panels show the subsurface offset common image geysers at x equals 1800 meters. For the surface seismic survey, most of the energies in the subsurface offset common image geysers are focused at h equals 0. However, in the VSP survey, the energies in the subsurface offset common image geysers are distributed along lines with slopes. We cannot tell whether the migration velocity model is accurate or not. We then transform the subsurface offset common image geysers into angle domain common image geysers using slant stack. Since the migration velocity model is correct, the events in the angle geysers are flat for both surface seismic survey and the VSP survey. However, only positive angles are present in the VSP survey. This is because the subsurface image points are on the left-hand side of the receiver line in the VSP survey. This is a recap of the cartoon illustration of the VSP survey. It is obvious that only one side of the receiver line is illuminated by source receiver pairs. This is the reason why only positive angles show up in the angle geysers in the right part. We then extract the subsurface offset common image geysers at x equals 2200 meters. The subsurface offset range is from -100 meters to 100 meters. In this case, the subsurface image points are on the right-hand side of the receiver line in the VSP survey. As in the previous case, most of the energies in the subsurface offset common image geysers are focused at h equals 0 in the surface seismic survey. However, in the VSP survey, the energies in the subsurface offset common image geysers are still distributed along lines with slopes. In addition, the slope information is different compared with the previous case. These are the angle geysers transformed from the previous subsurface offset common image geysers. The events in the angle geysers are flat, indicating that migration velocity model is correct. However, in the VSP survey, only negative angles show up because the subsurface image points are on the right-hand side of the receiver line. We then perform LSEITM with incorrect migration velocity model. The velocity errors are 10%. The subsurface offset range is from -400 meters to 400 meters. The front panels show the migration images at h equals 0. For the surface seismic survey, the horizontal reflectors are pulled up due to the slower migration velocity model. However, for the VSP survey, the reflectors in the migration profile become tilted. More distortion can be observed from the VSP image, although the migration velocity errors are the same for both the VSP survey and the surface seismic survey. This indicates that the VSP data are more sensitive to the velocity errors. The red panels show the subsurface offset common image geysers at h equals 1800 meters. Downward curvature appears in the surface seismic survey because of the slower migration velocity model. However, the behavior of the subsurface offset common image geysers in the VSP survey is significantly different from the surface seismic survey. We cannot follow the experience from the surface seismic survey to tell whether the migration velocity model is accurate or not for the VSP survey. These are the angle geysers transformed from the previous subsurface offset common image geysers. The events in the angle geysers are curved up, indicating that migration velocity model is slower. In the VSP survey, only positive angles show up because the subsurface image points are on the left-hand side of the receiver line. We then extract the subsurface offset common image gathers at x equals 2,200 meters. The subsurface offset range is from -400 meters to 400 meters. In this case, the subsurface image points are on the right-hand side of the receiver line in the VSP survey. As in the previous case, downward curvature appears in the surface seismic survey because the migration velocity is slower. However, in the VSP survey, we could not find similar curvature information as in the surface seismic survey. The subsurface offset common image gathers are then transformed into angle domain common image gathers using slant stack. The events in the angle gathers are curved up, indicating that migration velocity model is slower. In the VSP survey, only negative angles show up because the subsurface image points are on the right-hand side of the receiver line. In previous slides, we have shown that there are significant differences in the behavior of the subsurface offset common image gathers and the angle domain common image gathers. Due to these significant differences, we should be careful when adopting the successful numerical experiences from surface seismic data to VSP data. As an illustration, we apply the image enhancement strategy we have proposed for surface seismic data to the VSP data. In our previous study, we have shown that we can stack the subsurface offset extended images along the subsurface offset axis within the half-wavelength constraint. The resulting image is in better quality than the image at the zero subsurface offset and the image from conventional LS-RTM, especially when large errors are present in the migration velocity model. The left part shows the stacked image for the surface seismic survey, and the right part shows the stacked image for the VSP survey. This is the case for the correct migration velocity model. And this is the case for the incorrect migration velocity model. As you can see, the image qualities become much better after stacking for the surface seismic survey. However, for the VSP survey, the image quality degrades after stacking along the subsurface offset axis. These results suggest that it may not be suitable to directly apply the imaging algorithms developed for surface seismic data to VSP data. We then apply LS-ERTM to the same model. There are in total 30 sources on the surface from x equals 100 meters to x equals 3000 meters, with a source spacing of 100 meters. For the surface seismic survey, there are 438 receivers deployed on the surface with a receiver interval of 20 meters. For the VSP survey, there are 126 receivers at x equals 1500 meters in distance, from z equals 1500 meters to z equals 4000 meters at depth. The receiver interval is 20 meters. We first perform LS-ERTM with the correct migration velocity model. It is built by smoothing the true velocity model with a 21-grid Gaussian smoother. These are the LS-ERTM results from surface seismic data. The subsurface offset range is from -240 meters to 240 meters. The front panels plot the images at h equals 0. The shallow parts are dominated by high amplitude low wave number noises caused by backscattered waves. Because the same model contains strong lateral variations, we extract subsurface offset common image gathers at different horizontal locations. The right panel in the left figure shows the subsurface offset common image gathers at x equals 1000 meters, and the right panel in the right figure shows the subsurface offset common image gathers at x equals 2400 meters. Because the migration velocity is accurate, most of the energies in the subsurface offset common image gathers are focused at h equals 0. These are the LS-ERTM results from VSP data. The subsurface offset range is from -240 meters to 240 meters. The front panels plot the images at h equals 0. The salt flanks are more clearly resolved than those from surface seismic data, as shown in previous slides. However, The sedimentary structures are not widely illuminated, especially for the shallow parts. In the left figure, the red panel shows the subsurface offset common image gathers at x equals 1000 meters, where the image points are on the left-hand side of the receiver line. In the right figure, the red panel shows the subsurface offset common image gathers at x equals 2400 meters, where the image points are on the right-hand side of the receiver line. Although the migration velocity model is correct, the energies in the subsurface offset common image gathers are still distributed along lines with slopes. In particular, the subsurface offset behavior is quite different when the image points are on different sides of the receiver line. We then perform LS-ERTM with an incorrect migration velocity model. It is obtained by scaling the correct migration velocity model with a factor of 0.9. The bulk velocity errors are 10%. These are the LS-ERTM results from surface seismic data. The subsurface offset range is from -600 meters to 600 meters. The front panels plot the images at h equals 0. The shallow parts are dominated by high amplitude, low wave number noises caused by backscattered waves. The red panel in the left figure shows the subsurface offset common image gathers at x equals 1000 meters, and the red panel in the right figure shows the subsurface offset common image gathers at x equals 2400 meters. Because we are using a slower migration velocity model, downward curvatures appear in the subsurface offset common image gathers. These are the LS-ERTM results from VSP data. The subsurface offset range is from -600 meters to 600 meters. The front panels plot images at h equals 0, similar to the case using correct migration velocity model. The salt flanks are more clearly resolved than those from surface seismic data. However, the illumination area is much narrower than the surface seismic data. In the left figure, the red panel shows the subsurface offset common image gathers at x equals 1000 meters, where the image points are on the left-hand side of the receiver line. In the right figure, the red panel shows the subsurface offset common image gathers at x equals 2400 meters, where the image points are on the right-hand side of the receiver line. We cannot find similar curvature information as in the surface seismic survey. It is not obvious to tell whether the migration velocity model is accurate or not for the VSP survey. We then stack the extended images along the subsurface offset within the half-wavelength constraints. These are the results using correct migration velocity model. These are the results using incorrect migration velocity model. The left part shows the surface seismic image. The image quality becomes much better when compared with the image at 0 subsurface offset. The high amplitude, low wave number noises are effectively reduced. The sedimentary structures are clearly resolved. The red part shows the VSP image. It seems that the imaging of the salt body is enhanced. However, it is not easy to track the sedimentary structure information, so this image cannot be regarded as an improvement from the 0 subsurface offset image. These results further indicate that direct application of imaging strategies from surface seismic data could not provide satisfactory results. To conclude, we have applied LS-ERTM to VSP geometry. We noticed that the behavior of LS-ERTM shows significant differences in VSP data compared to surface seismic data. Because of the significant differences, when we apply the successful numerical experiences from surface seismic data to the VSP data, we could not get satisfactory results. Specific imaging strategies need to be designed for VSP data. This is the research topic for our future study. This is all of my talk. Thanks again for your attention. If you have any comments and suggestions, please let me know through this email.